Go, benzene. Right, okay, so benzene. Come on. So benzene was identified quite a long time ago, a couple of hundred years ago, I think by Faraday. And it was known as C6H6, and if you do your double bond equivalent on C6H6, what do you get? How many hydrogens would a fully saturated straight chain C6 compound have? 14. So DBE1 would be C6H12, 2 would be 10, 3 would be 8, 4. Double bond equivalent of 4, which means it's either got to have 4 double bonds, or 2 triple bonds, or 4 rings, and you can come up with some of these structures, and there are some of them in my topic booklet. Some of them are pretty crazy. I suppose that's not so crazy, is it? 2 rings and 2 double bonds, and so on. But it was Kekulé in, I don't know what year that was, a French chemist who came up with the idea of the ring, supposedly because he had a daydream about Ouroboros, the snake eating its own tail. Don't know if that's true. I think ringed compounds were probably fairly familiar in the 19th century. Anyway, so he came up with a ring of 6 carbons with alternating single and double bonds. So if you draw that out as displayed formula, you can see that every carbon has a single and a double bond, and every carbon has 1 hydrogen sticking out. Okay, which seems like a fairly reasonable attempt at a structure. And indeed, you will see benzene drawn as alternating single and double bonds sometimes in textbooks. It's pretty common, it's pretty normal, it's also pretty wrong. It's not the correct structure at all. So, what I want to start with really is why Kekulé's structure is wrong. And I'm going to present 3 lots of evidence about why the structure was wrong. And the first bit of data is substitution data. So if I pulled off a couple of, or substituted is the correct word, isn't it? A couple of hydrogens and replaced them with bromines, if Kekulé's structure was right, I should be able to make 2 different isomers. I should be able to get a substitution product where the bromines are either side of a single bond, and then we should have a compound where the 2 bromines are either side of a double bond. And they should be different. They would have different melting points and boiling points. They could be separated by fractional distillation and so on. But we find no such thing. If you do an adjacent substitution of a benzene ring, you only have 1 product. So that would suggest Kekulé is wrong. The second bit of data is bond length. It's relatively straightforward. Modern techniques using X-ray crystal diffraction to measure the length of a single bond and a double bond, carbon single bond, carbon-carbon double bond. These are not numbers I keep in my head. Single bond is 154 picometers, where a picometer is very small. What's pico? 10 to the minus 12. Okay, so Yeah, quite small. 134 picometers for the length of a double bond. Okay, so just looking at the numbers, single bond is a bit longer. Well, that kind of makes sense. You'd expect having more electrons in the overlap region of the covalent bond. It pulls the atoms in a bit more tightly. For benzene, all the carbon-carbon bonds are the same length. I'm going to draw it as a kind of 1.5, and they're 140 picometers. That's some way between a single bond and a double bond, perhaps a bit nearer to a carbon-carbon double bond. But I think the crucial information is that they're all the same length. If we drew a benzene ring, or perhaps I should call this cyclohexa 135 triene. Okay, if I was to draw a cyclohexa 135 triene molecule, getting the bond lengths right, well, it would kind of have short. Hang on, let's get this right. Very hard to draw. Okay, should have very short double bonds and very long single bonds. Okay, it wouldn't actually be a perfect hexagon. It would be a kind of sort of distorted hexagon shape. Yeah, it's not my finest moment, is it? Okay. Did you have a question at the back there?
Yeah, I was just wondering what you mean. Does that say benzene next to the C?
Oh, sorry. Yeah, it does. Actually, it says Benin because I spelt it wrong. Yeah, it's got a Z in it now. Thank you. It's a live show, folks. Okay. So, two bits of fairly damning evidence for the cyclohexane triene shape and Kekulé. Well, it's not looking good. The third bit of evidence is for hydrogenation enthalpy. What's hydrogenation? Well, it's just adding hydrogen. If I take cyclohexene, just a ring with one carbon-carbon double bond in it, and I add some hydrogen to that, and then that would make cyclohexane, and I look at the delta H for that reaction, adding two hydrogens across the double bond, it's minus 120 kilojoules per mole. Okay, so if I got two double bonds, and added two H2s to make cyclohexane, what would we expect the delta H to be for that? 240? Minus 240. Exothermic. So if we've got three double bonds, and this is all just supposition, logic, argument, then we would expect minus 360. Okay. If we actually do this reaction with benzene, I'll come back to that circle in a minute, minus 208 kilojoules per mole. So that's our, where's my red? 360 was our guess. 208 is the actual value that we find. And the difference between 360 and 208, it's not a small error, is it? It's not 5% or 10%. It's a big amount, but it's going to take a bit of explaining. But go on.
I was going to say, is the minus 120 a value you have to remember is like different for each question?
Does it matter what?
Do you have to remember the one minus 120?
You don't have to remember the values. You have to be able to work out that if it's minus 120 for one bond, then 240 and 360 for 2 and 3 bonds. But it's a good question. We'll come back to how this is asked in the exam. But they will give you the minus 120 and they'll give you the minus 208 and ask you to use that as evidence that this structure's wrong. Yeah, just to reinforce that, this is not just me talking around something, but because it's interesting. This is good 6-marker material explaining why cyclohexane 135-triene is not the correct structure for benzene. I just want to take this data and kind of re-display it in a sort of Born-Haber cycle kind of way. The Born-Haber diagrams with energy going up here, and then you don't really have an axis along there, do you? You just have a sort of a floor. So I'm going to put cyclohexene here. Okay, that's the energy of cyclohexene. And then let's put a bit of colour in this, otherwise it's going to get... So that delta H there, minus 120. Remember, exothermic reactions go down, don't they, on a Born-Haber cycle? So more energy up here. Things losing energy are going down. Losing energy to the surroundings, exothermic, means going downwards, endothermics, that way. So if cyclohexene is there, then cyclohexadiene would be up here. So again, that's our best guess. That should be around about minus 240. And then our cyclohexatriene would be up here. So we've got minus 360. And then what we actually find, so benzene's actually more, it's lower than the cyclohexadiene, isn't it? Yeah. Come back to cyclohexadiene in a moment. So benzene minus 208. Okay, and the reason I want to show this diagram on a sort of Born-Haber cycle thing is to really illustrate the difference we have here. This is the important bit. That difference there of 152 kilojoules is the difference between the actual structure of benzene and our imagined 3 double bonds in a ring. And that difference is not just a number. Benzene is lower than we would expect it to be. It's lower in energy than we would expect it to be. Therefore, it's more stable than we would expect it to be. You can't just have stability coming out of nowhere. There must be some sort of chemical kind of process going on that makes benzene more stable.
So with that 152 different, would that be a positive or negative?
So it's if we're measuring it downwards, I've put the arrow going in both directions, but it's 152 kilojoules more stable, so in the exothermic direction. So I suppose that would have to be minus, yeah. Yeah, but I always have a problem, is is minus 208 a bigger number or a smaller number than minus 360? The difference is not obvious. Okay, I'm just going to pull up the topic booklet here because it's got a bit of a diagram that I can't draw. So we're going to fill in a few late. Charlie, this morning. Yeah, okay. So I'll come back to that. I'm going to leave this on the board, this diagram. I'll come back to it. I just need to take a bit of a detour. And it's an interesting detour, I'm sure you'll find, but it's not all examinable. So I'll point out the bits which can be on the exam and the bits which won't. But just to start off, we think about the atomic structure of carbon, the electron structure of carbon. What orbitals does carbon have that have got electrons in? If I was to draw one of these, the energy diagrams. Here, we'll start down here with a 1s. What electrons would I have to fill? Sorry, what orbitals would I have to fill with electrons? 1s, yeah, we've got 1s2.
2s2 and 2p2.
Okay, and the 2p2?
It'll have to be the first two rows, one electron in each of the first two boxes.
Right, okay, so that's Hund's rule of multiplicity, yeah? The number of unpaired electrons should, in a given subshell, should be as many as possible. Okay, so did you ever wonder? Carbon has two different types of electrons in its second shell. It's got a couple of 2s electrons, and that orbital is full, that subshell is full. Of course, there are 4 gaps in the 2p, but the p electrons and the s electrons are quite different in geometry, in shape, in energy. I don't know if you've ever thought about what shape the orbitals are. S orbitals? What shape's an s orbital?
Is it just a sphere?
It's just a sphere, that's right. So we imagine that the 1s or the 2s, the 1s orbital is just a smaller sphere, and then the 2s orbital is slightly larger. What shape are the p orbitals?
Is it like 2 lobes?
Yeah, that's right. There's a pair of lobes that exist on the x, the y, and then the z lines of the axes there. So we've got a couple on the x, that will be the 2px, and then we've got a couple on the y, that's the 2py, and then you'd have a sort of three-dimensional thing going on here for the 2pz. So they're in those 3 dimensions there. So they're quite different types of electron, and I don't know if it's ever been shared with you that in the 2 lobes the electrons usually have an opposite state, sometimes referred to as spin, sometimes as plus and minus. Sometimes they're just drawn as green and blue. They have different states. How can you get carbon with 4 equivalent bonds to 4 other atoms, say 4 hydrogen atoms, when you've got a couple of electrons that look like that and a couple of electrons that look like that. How can they overlap with other orbitals in a way that gives you a precise tetrahedral, completely equal in all directions, 109.5 degree bond angle kind of way? You might have asked yourself at some point. You might have thought, hang on a moment, these p orbitals and these s orbitals have completely different geometries. How can you possibly arrange those to produce something equal? You might have thought.
Maybe on different planes.
What are we talking about? Planes of existence here? What do we mean?
If one of them, I was just thinking if one of the p orbital, sorry, was if it was in the direction of its axes and the s orbital was in a perpendicular.
You can't have a perpendicular. I mean,
Never mind. It's fair.
the s orbital is exactly symmetrical across all three axes. Okay. Well, go on. I'm really open to suggestions.
Hybridisation.
Just as a guess that there might be some sort of hybridisation taking place. Yeah, that's a very good guess, Matty. Yeah, well done. Do you want to go further with your hybridisation idea that you've just come up with?
The subcells like merge or something.
They merge, yeah. It takes a little bit of, as a sort of 1, 2, 3 step thing. The first step, you do not need to know this for the exam, so you can relax, okay, and just enjoy the logic, and enjoy the fact that if you did a degree in chemistry, this would be a lot what your first year is like. What happens is one of the electrons in the 2s is promoted up to the 2p. That's the correct term, promoted. It gets, higher salary in the 2p. And then the orbitals merge, hybridize, and we make 4 sp3 up there, hybrid orbitals. Hybrid is just another word for combination, isn't it? And now we can put 1 electron in each box, and we've got 4 equivalent orbitals. It's worth thinking about what they look like. If you overlap an s orbital with a p orbital, remember I said they're like different types. So you've got one lobe is plus and the other one's minus, and we're adding it to the s orbital, which is of all of the same flavour, plus or minus. So when they overlap, you end up with, and this is quite hard to draw, an orbital which is larger in one direction than in the other. So it's like a part of the lobe gets bigger because it's, what's that thing in physics where the waves reinforce? Not just called reinforcing. I don't know what that is. Where two waves meet each other and then the peaks hit the peaks and they.
Constructive interference.
Thank you, constructive interference. Thank you, and the pluses and the minuses cancel out. Anyway, so we'd have that, and then we'd have another one down here, and then another one down there, and then kind of one in the front. It's not the easiest thing to draw. Okay, something like that. So you end up with 4 sp3 hybrid orbitals, which get as far apart from each other as possible, 109.5 tetrahedral bond angle, and we're away. Okay, that's fairly straightforward. What's less straightforward is when you have a carbon-carbon double bond. Okay. Let's go back here. So a carbon-carbon double bond, and we're verging on the stuff that you need to know, so pay attention. Carbon-carbon double bond takes 2 of the p orbitals and the s orbital and combines them, hybridizes them. So we end up with with 3 sp2 hybrid orbitals, and then 1 p orbital gets left behind. Yes, Matty?
So, is this just in carbon, or is this happening in all elements?
I have no idea. If other elements can hybridize, that's a nice question.
What takes priority then? The p orbital or the s orbital? Like,
What do you mean by priority?
So you drew 3 blocks where in the 2s row,
Yeah.
1 block in the 3p row. How much only 1 block in the 3p row? It's 3 blocks. Are then electrons being sort of bounced down a level?
What?
So from the 2p orbital, so you've got your sp hybrid. Is that electrons from the p orbital? Is that making more s orbitals then? What?
No,
That's not answering the question then.
I'm not sure what your question is.
So, see we put sp hybrid. Is that the shapes of the s orbitals? Or is that
There's no
different shape?
shapes here. We're just drawing electrons in boxes.
Okay.
All orbitals, when we're drawing these diagrams, are represented as a box,
Yeah.
and each box can take 2 electrons.
So I need to know. Thanks.
Okay. Right. So stay with me here. So the 3 sp2 hybrid orbitals get as far from each other as possible, giving us what geometry? 3 clouds of electrons getting as far from each other as possible. Very nice. And what's the bond angle? 120, yeah, trigonal planar. So there's my 2 carbons there, and that's my flat plane, by the way. So we're on a trigonal planar structure, so you'd have an orbital there, an orbital there, and an orbital there, and those 2 orbitals overlap. By the way, where s orbitals overlap, it's called that's not the right symbol, it's called a sigma bond. S for orbital gives you S for sigma. And a sigma bond is where, you know that clouds of electrons overlap, okay? So that overlap region there would be the area where the covalent bond is made. And that's all in a flat plane. The p orbitals, however, remember the p orbitals can be sort of upright above and below the plane. The p orbitals kind of sit above and below that plane, kind of on top of or as well as the 3 sp2 hybrids. And then they overlap as well, and it's sort of difficult to draw this, but when the orbitals overlap, when orbitals overlap, they don't just kind of share a bit of space, they completely merge and create a new three-dimensional shape, which is called a molecular orbital. And again, if you do degree level chemistry, you'll spend a large part of your first year studying molecular orbital theory.
Is that what forms what you call a pi bond?
Right, that's your pi bond. Yes, where you have 2 p electrons overlapping. That's a pi bond. And the pi bond, you'll notice there's a pile of electrons above the plane, and there's a pile of electrons. Pile is probably the wrong word. Sausage would be a better word. There's a sort of sausage of electrons above and a sausage of electrons below the plane. And that's what makes the alkene susceptible to electrophilic attack, because we've got a bunch of electrons sitting on top of the alkene. Makes it very easy for positively charged things to get dragged in there. Are you all still with me? Great. Yeah. Yeah, you need to know the next bit, but the next bit doesn't make any sense unless you've had all of this. You don't need to know about hybrid orbitals, you'll be pleased to know. But you do need to know that the p electrons or the pi bonds form above and below the plane. And I struggled to draw this next diagram, which is why I've just gone to your topic booklet there. And it helps that it's in colour. Okay, benzene. Remember benzene? This is a lesson about benzene. Yeah. Remember that. Right. Okay, let's get rid of all of that. And try and work out what on earth is going on in this diagram. So, every carbon in benzene has a double bond. So every carbon would be sp2 hybridized, and that means that every carbon has a leftover, if you like, p electron, and the p electron exists in two lobes, which we've just coloured yellow and blue here, just to remind us that they're different. And the benzene itself is in a flat plane, so we've got a perfect hexagon of carbons, bond angle of 120 degrees all the way around. And then above and below that plane, we have the p electrons. And this is important. This is the stuff you'd need to know. So let's just note it down, carefully. So we've got six electrons, 6 carbon atoms in a ring, in a regular hexagon, with a bond angle of 120 degrees all the way around, and it's a flat planar molecule. All the atoms, including the hydrogen atoms, are in the same plane. Planar. Let's just really emphasize that. I might have to go and get another black pen. Give me a moment. And then each carbon atom has a single electron in a p orbital and just like in with the alkenes, with ethene, excuse me. Those p electrons above and below the plane can overlap, forming a ring of, keyword, delocalized charge. Now, wherever you get delocalization in chemistry, there's always a payoff, and the payoff is makes the molecule, makes whatever it is, more stable. Makes it more stable because if you keep all the electrons in one place, they're all kind of sitting on their own little atom and they're all feeling rather isolated. But if they can spread out and move around the molecule, they become much more relaxed, much more at ease. So that delocalization gives us extra stability. Stabilizes the ring, and we saw it stabilizes it to the tune of that 152 kilojoules per mole. So that's why when we draw benzene, drawing a hexagon with a circle in the middle is actually the most correct view of benzene. Drawing it with 3 double bonds really doesn't cut it. That's not what benzene is like. The electrons are delocalized in that ring. So the types of molecule where you have rings of delocalized charge, there are lots of them, hundreds of them. And they have a name. They're known as aromatic compounds. Now, aromatic doesn't really have that meaning outside of chemistry, does it? The meaning of the word aromatic is normally smells nice. You know, if you're talking about your coffee or your white wine, aromatic tends to mean, you know, notes of, I don't know, honey or whatever. I don't know. I don't really do kind of thing.
So is the representation of the delocalized ring a circle? Because if it was actually, hang on, and the reason of 3 double bonds not being correct is because you have technically all of the pi bonds overlapping. Could you see it's that way in a sense? All of the, no, I say overlapping, but
Well, so a pi bond is just when you've got a pi bond is just when you've got 2 p orbitals overlapping.
oh, just 2 p orbitals.
So
okay.
So yeah, we have got pi all the way around in a molecule that looks, you know, a little bit like a pie as well, or maybe a burger or a couple of donuts. Some sort of food. Well, we're not sure. But the word aromatic just refers to overlapping p electrons, delocalizing, stabilizing the molecule. It does bring up the question, though, if these molecules are aromatic, what are the other molecules called? You know, things like methane and butane, and what are they? Molecules that don't have any kind of overlapping, delocalized p electrons. What are they? And the word is aliphatic, which is a word I'm never going to use ever again. So aliphatic and aromatic are the 2 areas of organic chemistry. Aromatic being all the benzene, overlappy, delocalized, destabilized molecules, and aliphatic being everything else that's just a chain or a branch or whatever. All right. Is that enough? Your brain's full. Great. I will just say, I'll just make one little point, just because the next thing is naming, and if I just make this point, the naming might make a bit more sense, because if I just draw 2 compounds on the board, here we are. And this one's called, don't shout at once, bromomethane, and this one's called 2-methylpropane, which means that we're naming that CH3 part of the molecule. Oh, wrong bit. That CH3 part of the molecule is being named in 2 different ways. Sometimes we'll call it something methane, and sometimes we'll call it methyl something. And it depends upon what the CH3 is attached to. If the CH3 is the longest carbon chain, then it's something methane. If the CH3 is attached to a longer carbon chain, then it's methyl something. Benzene works in the same way. It's got 2 names. If I have a benzene ring with a group on it, where benzene is the most important carbon chain, then we use the word benzene, bromobenzene. But if I put a benzene ring on another carbon chain, then like methane and methyl, we go from benzene to phenyl. Okay, there's no benzyl anything, it's phenyl. Okay, so phenyl, what would that be? 2-phenyl propane. Okay, so hopefully if you look at the names of the molecules on page 7, so you've got things like nitrobenzene, methylbenzene, chloromethylbenzene, and then we've got phenyl ethanone, phenyl ethene, phenyl amine. So we've got kind of two ways of looking at the benzene ring. But if you remember methane and methyl, then benzene and phenyl hopefully will make a bit more sense. I'll stop there before your heads explode. That was fun. Let's do it again sometime.